Every time we use an app, we're basically putting a ton of trust in the database behind it. Platforms like MongoDB are supposed to be these secure fortresses, right? Holding everything from our logins to our most personal info. But what happens when tiny, almost invisible cracks start to show up in those fortress walls? Well, let's take a look. So, here's our game plan. We're going to start with the ideal, the promise of perfect security. Then we'll dive into the discovery of two very different and very real vulnerabilities. We're going to see exactly how they worked, how they got fixed, and what the whole saga tells us about the constant battle to keep our data safe. All right, first things first, you got to understand the promise. Modern databases aren't just glorified spreadsheets. No, they're engineered from the ground up to be these complex security architectures, literal fortresses built to protect our most valuable data. And this right here really shows you what I mean. MongoDB, for example, talks a big game about its complete end-to-end security model. We're talking about controlling exactly who gets in the door, scrambling the data with encryption so it's useless to outsiders, and keeping a detailed log of everything that happens. This is supposed to be the gold standard. And believe me, the stakes are unbelievably high. This quote from MongoDB's own security documents just puts it all into perspective. $6 trillion. This isn't just about protecting a few files. It's about defending against a global criminal industry that's bigger than the economy of most countries. Getting security right is absolutely everything. Okay, but here's where that shiny promise smacks right into reality. Because even in the best designed fortress, the sheer complexity of software today means that hidden flaws can sit there for years, just waiting for someone to find them. And we're about to look at two perfect and pretty scary examples. We're going to dig into two fascinatingly different bugs. The first is a really subtle information leak, a super clever attack called Bigfoot. The second one? It's a critical memory leak called MongoBleed, and it's basically the exact opposite of subtle. It's more like a sledgehammer. So let's start with Bigfoot. This is a brilliant example of something called a side channel attack. Now, instead of trying to brute force the encryption, which is super hard, a side channel attack looks for clues in how the system works. It's like instead of picking a lock, you just listen really carefully to the clicks it makes when the key turns. This attack makes encrypted data talk without ever breaking the code. Now to get this, we need to talk about the write-ahead log, or the wall. Just think of it as the database's short-term memory, or its scratch pad. Before it makes any change permanent, it first scribbles a note in this log saying, hey, I'm about to do this. That way, if the power goes out, it knows exactly where it left off. This little log, it's the key to the whole attack. So check this out. This is the really clever part. The attacker doesn't need to break into the database server. All they need is access to the storage layer, like the hard drive. They can't read the encrypted log entries, but they can see how big they are. So a small change to the database creates a small encrypted log entry. A big change creates a big one. And that tiny difference in size, that's the leak. And look, this isn't just a theory on a whiteboard. Researchers proved they could use this size leakage to figure out actual sensitive data. For example, by looking at the size of a log entry for a new customer, they could guess the length of the city name they entered. That alone drastically narrows down where that customer might be. It's a silent, subtle, but incredibly powerful leak. All right, now let's switch gears completely to our second vulnerability, MongoBleed. If Bigfoot was a clever spy listening for whispers through the walls, MongoBleed was like walking up to the bank and finding the vault door just hanging wide open. This was a direct, critical bug that basically gave attackers a backstage pass right into the server's memory. And the potential scale of this thing was just staggering. When the bug was made public, security researchers scanned the internet and found over 213,000 MongoDB databases just sitting out there, connected to the web and likely vulnerable. This wasn't some niche issue. It was a massive, widespread problem. The reaction from the developer community really said it all. I mean, this quote from a user on Reddit sums up the shock perfectly. The idea that a bug this bad could just sit there, in the open, in the code, for nearly a decade without anyone noticing, it's just, as they said, absolutely insane. It's a huge reminder that just because code is open doesn't mean people are looking at the right parts. So how did it work? It was almost laughably simple. An attacker sends a specially made compressed message. The server tries to decompress it, but there's a mismatch in the size, which causes an error. But here's the fatal flaw. The error message the server sent back didn't just say, oops. It included a chunk of raw data straight from its own memory. That memory could have anything: user passwords, credit card info, session tokens. And the absolute worst part, you didn't need a password. No login, no authentication. Anyone could do it. Okay, so you've got these two massive flaws out on the open. What happens next? Well, the race is on. This part of the story is all about the response, the developers scrambling to engineer fixes, and the thousands of users out there rushing to get them installed before it's too late. This table really just lays it all out, side by side. You've got Bigfoot on one hand. It's subtle, it uses metadata, the size of things, to infer information. And on the other hand, you have MongoBleed, a direct punch to the gut, using a broken message to leak raw memory. Two totally different approaches, both leading to really serious consequences. Now, the fix for Bigfoot was just as elegant as the attack. You can see it here. Instead of writing logs that change in size, the new system takes every write, chops it up into segments that are all the exact same size, and adds a little bit of padding to the end if needed. So now, to an attacker who's watching, every single write looks identical. The information leak is gone, sealed shut. It's beautiful. But patching software in the real world is never that clean and simple. This comment from a developer really captures the chaos of the MongoBleed fix. They pushed it out super urgently, right over the holidays, with no warning. And at first, it felt like this crazy overreaction. But once everyone realized how bad the bug was, yeah, it was completely justified. So, after all that, what's the big lesson here? This isn't just a story about two bugs in one piece of software. It's really a story about the nature of security itself. It's a nonstop battle, and there are some really critical lessons we can pull from all this. So let's really boil this down. First, Bigfoot taught us that encryption isn't a magic wand. These clever side-channel attacks can still leak data. Second, MongoBleed hiding for a decade proves that source available isn't a guarantee that bugs will be found. And maybe the biggest lesson of all, the fact that over 200,000 servers were vulnerable in the first place shows that basic security hygiene, like, not pointing your database at the public internet, is still your single best line of defense. And of course, you have to keep patching, always. Which really just leaves us with one final and kind of unsettling question. Finding a bug like MongoBleed was a huge shock. It makes you wonder, right? What other decade-old, terrifyingly simple bugs are just lurking right now in the critical code that all of us rely on every single day?